Thank you very much for the SLC for this invitation for the talk. So I will talk about the cruise to the fast radial burst origin from the fast radial burst 2022-0509A. And when we mention the cruise to why does it work? Okay, when we talk about the cruise to fast radial burst origin, the first thing jumping to our mind is the magnetar within our Milky Way. But recently, one more repeating fast radial burst, especially the fast radial burst 24-114A appears. It seems the only especially isolated magnetar is not able to solve the fast radial burst problem. So we need more information about it. So here is, let's have a basic grasp of this object. For this fast radial burst 2205-29, this one we have observed was discovered by Try, and we monitor it with FAST and PAX with totally around 200 hours. And located with the very large array from the USA, and got the spectrum of the host galaxy and localized it to a redshift of about 0.2. So with our observation with the FAST, here shows the total observation time and number of bursts we detected, and fast radial burst rate we have, and the dispersion measure, and linear polarization degree, and the rotation measure of it. We see there was two bursting phases here, which the maximum rate around 200 per hour. And in the first 1.5 years, nearly every time we will observe it, we are able to detect it. And for people who may not very familiar with this rotation measure, in fact, it's the Faraday rotation effect, which make the polarization angle to rotate with the magnetic field and electron density, which means this rotation measure is able to prove the magnetic field and electron density within our line of sight. So if we see this value, see this change, we can see it fluctuated between -300 to 300 and have many reversals. So the standard deviation of it is around 100. And in the end of 2023, it seems we was not able to detect it in around one month. But after this 1 month, suddenly it come back. And the amazing thing appears is the rotation measure jumped to 2000, which is 20 times the standard deviation. And then within 2 weeks, it jumped to the baseline and stay in the baseline and for a long time. So by definition, we know this rotation measure is a measurement of the magnetic field and electron density within our line of sight. So the problem is, in fact, what is the plasma, and especially magnetized plasma, goes through our line of sight. So we go through different models with the Ockman's rule, from the very most simple model to one by one become a little bit complex. So our first graph, a fast radial burst will related to a magnetar. So the most simple model related to it may be the magnetar flare. But a magnetar flare usually composed of electron position pairs. So, and also observationally, within our Milky Way, the magnetar which produce the FRB, the rotation measure does not change during the bursting phase and not burst phase. And what's more, even if we have a high energy magnetar flare, if we expected the light curve to be a polar, right? Because the density and the size will decrease in a polar format. But what we observe is there is a plateau in the beginning, which is not able to be fitted by a polar. So magnetar flare is hard to explain this phenomenon. And usually a magnetar will reside in a supernova remnant. However, a supernova remnant will make the rotation measure to decrease in a very long time. But what we have is too weak, which is not able to explain it. But what about fluctuations? In fact, the fluctuation we predicted a polar in the polar format in the structure function, but what we have need a two component. So this armor flare is not able to be explained by normal turbulence. In fact, if we studied in more detail, it is still possible the filament in the here is able to observe it by order of magnitude estimate, but the chance of coincidence will be quite low. Then, since we are not able to explain it by a single magnetar, what about we have a companion of it? In fact, in our Milky Way, the next one, the Kavya, we are talking about the pulsar within a binary system, something like this. In a pulsar binary system like this, sometimes people see rotation measure change, like a little bit like what we see. But if we study it in a more detail, we will see what we have is 2 weeks of detection and more than 2 years observation. It will predict an eccentricity very high. So such high, it's very hard to be explained by the example that we have. So probability will be very low, and what's more, it will have a very strong prediction. The armor flare, what we see, should be periodic if this is the case. But it's still possible, and I would so I'm really looking forward to Kavya's talk next and try to compare these two systems. And what's more, if we expect a companion nearby, a companion usually have different activities, such as coronal mass ejection, like this image. If a companion produces a coronal mass ejection, and this is the postulated burst source, what we have. When the CME goes through our line site, we can see something similar to this. Here is an example from our solar CME. Here shows the physics picture. Here is the sun, and the orange and blue are two CMEs from the sun. Here is the background source. In fact, it's an AGN. People measure the rotation measure of this one, and for different time, you can see the rotation measure change and go back. As if we ignore the amplitude is quite similar to what we have. So based on this similar physics, we try to fit this process, and what we get is we are able to fit the rotation measure evolution what we get very nearly perfectly. And the parameters we need is a normal star with a high magnitude or a star with a massive CME. So this kind of system, this kind of CME are able to see in some binary systems or joint stars or something in fact in between. So for a very simple summary for this part is what we detect Armstrong and it decrease. It's very significant. It's higher than 20 sigma, and it prefers a binary system. And in fact, within this fast radial burst, if we exclude this flare part, and we see, take a look at the baseline part, you will see it seems the change here have some pattern. So we examined this baseline part, and it seems there is a periodic rotation measure behavior So the significance is around 3 to 4 sigma. So if this is true, then what can we get? Well, we can imagine if its companion have some wind going outside, so the wind will contribute to this rotation measure. In that case, we can estimate the magnetic field and the mass of the companion. What we need is a magnetized normal star or a massive normal star. In fact, we can also fit it with intermediate mass black hole, but the problem is where will be the source of accretion. So a summary for this phenomenon, again, we need this kind of companion. So it seems we have two pieces of puzzles, and this one have 20 sigma, and this one is 3 to 4 sigma. They match each other very well. What the companion parameters, what they need quite match each other. But very interestingly is for this object, we mentioned that time observed it also for such a long time. Here's the time's result. For long time, it seems in the dispersion measure, the time get by time have a decrease. And the decrease is not very significant, not very large, but the value is still significant. So this kind of phenomenon was also seen in, the other very famous oscillator burst. It seems it's indicating whether it's indicating there is a supernova remnant around it also. So it makes things very interesting and puzzling. Seems we have different evidences. We have evidence about isolated magnetar. At least we believe it is related to isolated magnetar. We also have different evidence about the periodic rate, and also from the host galaxy and the time catalog, which mentioned by this morning's talk. People, it seems, need something linked from this distribution. As an evidence of binary system, what we need, and also some evidence like declining dispersion measure and persistent radial source related to seems to support a supernova remnant origin. In that case, which could be the true physics what we have? Whether we need different channels, like an example of model is from Guiyang's cosmic comb. In different cases, we are able to produce fascinated bursts. Or we should try to combine them together to have a unified model. And Professor Wang will talk about it in more detail tomorrow. And in order to examine it, we're trying to find more evidence in other fascinated bursts. So searching for the rotation measure flare in other repeating fascinated bursts. In fact, it seems it's not easy to get a significant signal as what we have in 2022-05-29A, but still we have some very tentative signals. Although they have different problems, such as this one, it has only 1 point, and for this one, whether it's able to be explained by binary system also. And for this one, the 121102, the total amplitude is very high, so it's hard to say whether it's a fluctuation or it's true. So the search also, although these candidates are not convincing, it tells us why this kind of phenomenon was detected in this object for the first time. There are 3 reasons. One is this one have very long active durations. Currently, it's more than 2.5 years. So we have more values. We are able to see to get very real evidence. And also, if the observed radio of it is very high, then the behavior will be covered by fluctuations. also it seems the bursts during the atmosphere are not very bright. Even what we have in 2011-02, these points out was also get irreversible. So these bursts were not that bright. So if we combine all these things we currently know, what we have is we have different signals, and these two, the first two, give us it seems to be two pieces of puzzle and fits very well. Tells us if the object is related to a binary system, but also maybe it's also related to some supernovae remnant. And in other maybe possibly burst, it seems we have some tentative signals, but we don't know yet. So what we need here is what we all know and we are looking for in the future. As maybe we need also more detailed modeling, when we need to combine them together or they are multi-channels, and more observations to different phenomena of it and similar phenomena in the other possibilities. And maybe also multi-wavelength observations will also help us firstly, the host galaxy phenomena, but may help us to select between the magnetar, supernova remnant, and binary system. And also, we don't know, maybe in the future we are able to detect multi-wavelength signal from very nearby possibilities. Okay, here is my summary. Thank you. Observationally, we are not able to see the here. So it's not completely. So you don't see what and for everything, the little is able to reach the with no other tomorrow, but the key why it's excluded is magnetic field because well magnetic field on the outside, the electric field going down that magnetic field going down that. So what we detect is not we can only talk is not able to be reached by the road. But if it can be it by second, yes, it's quite hard. As far as 20. So for polar, it is nearly impossible, right? So it's quite hard. Okay.
Hi everyone, I'm Kavya Shaji and I'm a PhD student from University of Sydney working with Ninisha and Helen. So today I'll be briefly talking about my ongoing project focusing on this binary pulsar system B1259-63. I've been doing this project with a few people in this room including Kaustubh and Marcus. So the main aim of this project is to understand the system itself and also to explore whether systems like these can explain different properties we have seen in repeating FRBs and what fraction of repeating FRBs are currently consistent with being produced in similar environments. So just for the purpose of setting the stage, this pulsar, okay, it doesn't look proper, but it's okay. Can we see the PDF? Thank you. So this pulsar was initially discovered with Parkes high-frequency galactic survey by scientists back in 1990. So the system consists of a very young radio pulsar in a highly eccentric orbit around a O-type star with the orbital period of 3.4 years and with an eccentricity of 0.87. This star has a beady star-like equatorial disk, which the pulsar crosses twice over orbit, because the orbit itself is inclined with respect to the disk. During these two disk crossings, pulsar exhibits dramatic variations in propagation effects, including variations in RM, rotation measure, dispersion measure, scattering, and depolarization. Also, the pulse emission from the pulsar is eclipsed close to the periastron. We think it's due to scattering and effects of free absorption into this. So the recent periastron passage of the system was in June 2024. We observed this source with Meerkat and Urea for months bracketing the periastron passage, and we had near daily cadence observations close to the periastron. And because of our cadence, we were able to pinpoint the radio eclipse interval highly accurately. Specifically, the end of the eclipse was we were able to identify with an uncertainty of 0.1 days because we had multiple observations on the same day. So if we assume the second disk crossing happens when the eclipse ends, then by using simple Keplerian geometry, we can also calculate when must have first disk crossing happen. And it is around 19 days before the periastron. So with our observations, we were able to tightly constrain this crossing and periastron eclipse interval in 2024. So now we will look at some propagation effects variations of this pulsar close to periastron. So here I am showing the dispersion measure plotted against days relative to periastron with the different markers showing detections from different telescopes. So the median value of the dispersion measure away from the median value of the dispersion measure away from the periastron is 147, but as it approaches periastron, it has shown to increase by around 11 dm units above the baseline value. And after the periastron also, the dm remains elevated, but it is not as high as it was before the periastron. The overall increase in DM close to the periastron can be explained by the increased density in the disk and also the stellar wind. But why do we see this asymmetric variation? Same story for scattering as well. Far away from periastron, we see scattering time scale about like 0.7, 0.5 milliseconds. But as the pulsar approaches periastron, it peaks up to tens of milliseconds. So one epoch where we see significant scattering is shown in that top right plot where I have shown both the main pulse and interpulse from the pulsar. After the periastron, if you see, you can see the scattering fell back much sharply compared to the rise before periastron. This is the rotation measure values plotted against days related to periastron. The open diamond marker shows epochs where we had detections, but it was completely depolarized. So we do not have measured values of RMs. So before periastron, we saw RM increases by 2 orders of magnitude, then exhibited one sign reversal. But after the periastron, again we see erratic changes in RM with 11 sign reversals. If we assume the decretion disk of the star is like toroidal and smooth, we expect to see one sign reversal per periastron passage. But we see multiple sign reversals after the periastron passage, which is something we need to explain. So as I was discussing before, we see significant depolarization. So the polarization fraction decreases with the decreasing frequency, as I shown in this figure on top left. If this is due to different RM values within the same Faraday screen, we should see the polarization fraction following the Burns law, where we will see the polarization fraction decreasing exponentially with the wavelength to the power 4, quantified by the sigma RM, or also called as RM scatter. Here I am just plotting the RM scatter against days related to periastron. RM scatter increases as the pulsar approaches periastron, and it again shows like erratic changes in its values even up to 70 days after periastron. Here I'm just showing this RM scatter of 1259 compared with values seen in other repeating FRBs. So these values I have taken from literature, and I just reconstructed this curves using Burns law and assuming 100% linear polarization for repeating FRBs. So the purple, the magenta, red, and orange line shows the depolarization seen in 1259. So it's just saying that like a pulsar moving through a decretion disk of a PD type star can produce one of the key signature we see in repeating FRBs. Just summarizing all of the propagation effects we are seeing, we were seeing close to the periastron passage in 2024. The DM and scattering, also depolarization, rises and exhibits higher values before periastron, but RM exhibits sign reversals and erratic changes after the periastron. This actually means that we might be seeing different disk environments before and after periastron. So the question is, what causes this asymmetric variations in the propagation effects? Of course, one possible reason is the geometry itself, and also when the pulsar passes through approaches to periastron, the relativistic outflow of the pulsar can interact with the disk material or the stellar wind and form a bow shock. And if we are seeing the bow shock, the magnetic field structure and also the density within that will be different from that of the disk itself. So here I'm just showing our interpretation of what we think this asymmetry is coming from. So the diagram on the left side shows the system as viewed from Earth. So if we assume the eclipse interval marks the disk crossing, then we can see that the first discrossing happens a little bit closer to the star compared to the second discrossing. But that means in the first discrossing, we see a bit extra dense and turbulent environment. But this can't just explain the observed variations and sign reversals after the second discrossing. So there should be something else also at play. So we think it's the effect of Bohr shock as well. So before the Periastron, during the first discrossing, the Bohr shock must have already formed, and we might not be seeing it directly. In that first discrossing, we will be still seeing the pristineness and the DM and scat, everything coming from the disk itself. But after the Periastron, our line of sight must be seeing the pulsar sitting within its own Bohr shock cavity. So we will see lesser dense environment and lesser DM and lesser scattering. But if the Bohr shock itself has magnetized structure, and if it can contribute to RM, and or if it can somehow create multiple RM sign reversals, then Bohr shock can explain the RM sign reversals we observed till 70 days after the estimate. We still don't know what mechanisms at play which contributes to this erratic changes in RM, but if you have any insights on it, I'm happy to talk about it later. Now, repeating FRBs coming from massive star magnetar binary systems have been like invoked in many recent models to explain the periodicity, RM sign reversals, and also like RM layers. So the model is simple. So the magnetar is actually orbiting around a BE star with a decretion disk. But what produces FRBs in these models is still agnostic. So, but whatever be the mechanism of producing FRBs, if it's traversing or if it's orbiting on decretion disk, then we should see TM, RM scattering and depolarization. Everything changing in every orbit, like should show periodic modulation and track one another. We might see RM and DM peaking at one phase of the orbit, then rotation measure exhibiting variations at another phase of orbit, depending upon the orbit geometry, as we have seen in 1259. And if you think all the repeating FRBs are produced at similar origins, like in same environment, then the 121102 or 19052 where we see decreasing dispersion measure, PRS and everything, we will have to think like the binary system itself is completely embedded within a supernova remnant or magnetomic nebula that produce the magnetar. And the continuous decreasing dispersion measure is dominated by the supernova remnant itself. We heard yearly stop, and we know whole story about 2025, 2022 of 2029 now. It's a similar cases for other two repeating FRBs as well. So these are the three current repeating FRBs, almost or broadly consistent with 1259 like environments. We see RF layers, also like large depolarization, and also the different propagation effects tracking one another. But the main point here is that all these flares and everything have only happened once. It never occurred again. So only with continued monitoring, you will be able to see whether these are repeating again and again, and are we seeing any periodic modulation propagation effects. Yeah, we need more long-term observations of these sources to confirm. I'll leave it here and take questions.
He's asking if you can capture the zero piece.
Oh, like
Yeah.
oh, we haven't seen any evidence of emission in the system because it's not within the erosion of so yeah, there's no significance of emission
Okay,
For this system, we don't see any evidence for the continuous decreasing dispersion measure. We only see these kind of like enhancement close to Periastron. Change in what?
you see the walls in the water, you see any all information.
Oh, these are the solid dimension patterns of the yeah, into the past.
Okay, let's figure out the next thing I'm sure you
I think the one. Yeah.
Let's do
Yeah.
let's to turn up.
Okay. Right. This one.
Yeah, yes, this one.
Yeah, thanks.
No, yeah.
All right. Yeah, hello everyone, and yeah, thank you so much for having me, giving this opportunity to talk to you all. Yeah, so today I'll be talking about an interesting radio burst, or a few interesting radio bursts that we saw from a radio quiet neutron star in the galaxy, and which has some pretty interesting implications for fast radio bursts. So yeah, I'm just gonna start off with kind of an overview of models. I guess if I were giving this talk back in 2013, there would be about maybe 50 more slides about the period. But I think there's still some very interesting and popular theories out there. You kind of split them up into two basic things like magnetospheric origin for FRBs, or like shockwave models, which are kind of far away from the progenitor. But I think so far observational evidence is suggesting that neutron stars might be very, very promising candidate for explaining at least some of these FRBs. And specifically, I would say so these so-called magnetars, right, where we believe these are neutron stars which possess a much larger magnetic field, which is the energy reservoir to power them. But the thing is that if you look at the current population of neutron stars, right, which is nicely shown by this period derivative diagram, I wouldn't read too much into those lines of constant magnetic field. But you can see that they come in a lot of flavors, right? I mean, magnetars, these so-called magnetars we know are like very energetic, they're producing a lot of emission at higher energies. But there are some other neutron stars which are kind of atypical compared to the radio or pulsar cousins, but also show some higher energy emission. They're also like thermally powered. And so just to kind of go through a few of these subclasses of neutron star populations, of course, I start off with magnetars, which are in the top right corner there in the PP dot plane. But then we also have these so-called X-ray isolated. So there's a small population of these that are mostly majority of them are radio quiet. So we've tried to look for radio pulsations from them. But we definitely see pulse X-ray emission from them. We see that they have these thermal soft X-rays that are emitted from the surface of the neutron star. So thermally powered. But then we also have some more interesting populations like the central compact element, where you have these neutrons embedded in the supernova. But interestingly, unlike the the Crab pulsar, which is also a supernova, a very bright radio pulsar. We don't see radio emission from them, right? It's only if the first CCO, like very recently, that has changed because we saw actually very faint radio emission from a CCO, thanks to Meerkat. But again, these are X-ray sources, so we know that they're interesting. There's some kind of an extra source of energy in them, probably a little bit more energetic than their radio pulsar cousins. So that kind of begs the question of that maybe if we monitor not just these magnetars, but some of these more interesting subpopulation of neutron stars with radio telescopes, we might end up with some very interesting bursting phenomenology, even at radio wavelengths. And I think there's some credence to this statement just based on some previous evidence, right? I mean, first and foremost, we have the geomagnetic cloud. So which gave out one of the brightest radio bursts that we've seen in our galaxy. In fact, it was even contemporaneous with an X-ray burst. Similarly, I think Marcus mentioned this magnetar, his favorite magnetar, 11547, which is also showing some of these intermediate luminosity radio bursts, which are kind of in this gap, the so-called gap between, this observed gap in luminosity between radio pulses from neutron stars, which is kind of shown by this plot here. So, and similarly, SGR 1935 has also shown these bursts, right? And one of the interesting things that kind of sets these bursts apart are not just, of course, their radio emission properties and their luminosity itself, but also the fact that they've been seen at random rotational phases in the neutron star, which is unlike the pulse coherent radio emission that we typically see from neutron stars. And so it's quite important that we not just monitor all of these sources, but also kind of keep looking for sporadic radio bursts in our galaxy. And wide field radio surveys are exactly allowing us to do. The reason that we've kind of started to discover more and more of these very sporadic wide radio bursts, that we have seen a few now in this conference, is because we have these wide field radio surveys now that are scanning the sky continuously in real time, looking for these interesting radio bursts. And that's exactly what happened with Meerkat. So in February of 2024, when Meerkat was observing a very special part of the galaxy, the Eta Carina Nebula, we in Meerkat detected this burst. So, so this is the, this is the detection, right? The discovery of the burst. And Meerkat has a transient buffer, which means that we were able to save complex channelized voltages when we triggered on this burst. So what that meant was that we could go back, form visibilities, and actually create millisecond integration radio images of this region. And that's what this is shown over here, right? You can see these are two snapshots, one where the burst is on. You can see here there's a little bright spot. Here there's nothing. If you take a difference, you can see there's a nice burst that is localized to our second visit. So we managed to localize this, which is interesting. And it just so happens that it sits right on top of a well-known X-ray loud neutron star candidate, which has this extremely memorable name. And it's been, it's been a well-known source. It's been followed up a lot using the XM Newton telescope. People have looked for periodic signals in X-rays. People that have failed so far. There's been an 18 millisecond candidate, but that candidate period was never confirmed in follow-up observations. But the fact that we saw a radio burst that is coincident with this location to within an arc second basically confirmed one, the neutron star nature of the source. And that's kind of interesting because it's a radio quiet neutron star, and we're seeing this really bright sporadic radio burst from this source. Now, if we talk, so this is before I go with the burst itself, there's still a question of if you say, okay, it's a neutron star, but what kind of exactly? So I showed you those two sort of specific subclasses before. Even though, so those two subclasses do share a lot of their X-ray spectral properties. But one of the, so the two key identifying features, one is an existence of a supernova remnant, and also the period. So typically CCOs tend to have millisecond period because they're faster because they're younger objects still within their supernova remnant. On the other hand, isolated X-ray pulsars typically middle-aged, much slower because they've had time to spin down to longer periods. But a lack of period means that we can't really say what kind of neutron star this is. And also, if you look at so that's a multi-wavelength image of the region. So that's the location of the radio source with the infrared image, and overlaid contours are the radio emission. So it's as you can see, it's a crowded field, right? It's a star-forming region. So figuring out if there's a supernova remnant there is quite challenging. So yeah, the jury's still out there. So if we look at this first burst, right? So this is the first we discovered in February. And because of the transient buffer data, we were able to kind of get, re-beamform this and get a high time resolution dynamic spectrum. And you can see it's very interesting, right? The morphology. You have this really sharp rise in this initial peak, and then you see these multiple components. And you can also see, okay, now this seems to not work. That's fine. But you can see different components kind of showing up at lower and lower frequencies. We definitely know it's not scattering because the narrow component, as you can see, is pretty broadband, and you see no evidence for scattering right up to 1,000 megahertz. And you can think of this as, it's again showing some properties very similar to what you see in repeating FRBs, where you have multiple components kind of showing up at different frequencies. So spurred on by this, we decided to follow this. So we looked for green time, 64-meter Marianne telescope. Along with that, we also applied for some dedicated green time on this source. And so that's just showing kind of roughly our cadence of observing. And I'm going to talk about that date, April of 2025 there, because that's when we saw this second radio burst from the source with the bar. So here I'm showing you the dynamic spectrum for the Meerkat and the Marianne telescope burst. You can see that morphologically they're roughly similar, where it shows this very, very narrow, very bright first component, and it shows the different components kind of, which are much fainter. But interestingly, you can see that in the components are distinct in the Marianne burst. And you can see this one, especially, it's kind of drifting down at a different DM when you align all the other components, which is very similar again to some of these repeating FRBs where we see these drift bands, and you see sometimes every now and then one of the components is misaligned with the rest of them when you disperse them at a specific DM. So if you think about, so it seems like these sporadic ones, they seem to share a lot of observed properties with repeating FRB bursts. Now, of course, there's the question of luminosity here. So if we assume that this is something different from the pulse coherent radio emission that you see from pulsars, and if you think that there's some kind of an emission mechanism that's magnetically powered and some fraction of that magnetic energy is dissipated in these radio emission, you could maybe think of, if there's a diversity or a big range of magnetic fields that neutrons are possessed depending on where they are on the evolutionary tracks, you can kind of think of a continuum in the luminosity from these sporadic radio bursts that you would get, which will help us in filling up that gap, which is already kind of we're starting to fill that up already with some of the magnetars and some of the other of these interesting neutron stars that we have. So those two stars, by the way, are these two bursts from this specific source, just to be clear. So with that, I think I'm going to end with my summary. I think the main point here that I'm trying to drive home is that I think it's really important that we monitor most or all of the neutron stars that we see in our galaxies, not just with these wide field surveys, but also dedicated monitoring with these small dish radio telescopes, because these bursts are bright enough to be seen with any modestly sized radio telescope. And so small dishes monitoring specific sources, even if they're radio quiet, is going to be highly, highly valuable. Because I feel like if given enough time and enough monitoring, I think we'll be able to fill up that luminosity gap pretty quickly with these kind of really bright intermediate luminosity bursts. That will give us a lot of insight into connection between neutron stars and these. So yeah, with that, I'll end there. Thank you so much. So this was not a part of any dedicated monitoring campaign because you're observing immensely, right? So we are just kind of at the mercy of whoever wants to observe whatever part of the sky. We are just lucky that when this part of the sky was being observed on American. Actually, it's kind of funny because the actual observation was to look at a magnetar in the same part of the sky for radio pulsation. And we found a radio version this year, which is a separate source altogether. So yeah, which is kind of funny, but yeah. Yeah, so they're both not highly, like, there's not a very high degree of linear polarization, so I would say it's like, so they're roughly at anywhere between 30 to 50% linearly polarized. The first one actually, especially in the narrow component, shows a very nice S-shaped sweep, and then it kind of flattens out. And that's something very similar to what we see in the second burst as well. Although we didn't get enough signal to noise in the trailing components because they were not as bright as the other one, and so we didn't have enough to get actual good values for the PAs. But yeah, they're roughly consistently. So there's this class of these objects called the Magnificent Seven. But I think a lot of them are unfortunately sub-standard. There are a couple, including this one. I think there might be like 3 or 4 of these definitely.
Okay, this is second. Thank you. About the industry, actual FRB,
Okay. Hello everyone. I'm Jun-Shuo, a PhD student from NUC, and I'm glad to share our work about prolific repeating faster reduced source FRB 2024/14A, and it's may lead energy increases of magnetar models for this source. So Wang's talk has introduced the fast FRB KSP, and under the collaboration, we detected more than 30,000 bursts of repeaters, and among them, about half of them from our source. Oh. Okay. Jerry has introduced this source, and it is discovered by Chen and also known as R147. And we follow up it since January 28th, 2026 to 2024. And we detected several bursts. And then in March, we detected a burst storm. Most results were posted to the ATL. And one of our collaborators, Xiangli Chen, has measured the redshift of the host galaxy with a GTC telescope. So the fast monitoring this source from January 2024 to now, and lasting for about 2.5 years, totally observing time of 70 hours, and we detected more than 17,000 bursts among this period. So this source keeps active for about 500 days during our monitoring. And there are 4 high active places with a very high burst rate. The control tried to search for a period and detected a possible period of 143 days. And we tried to analyze this first 200 Compagation and do the detailed analysis of 11,000 bursts included. And we calculated each burst, each energy of each burst, and there shows no significant evolution trend of the helium median energy. And for as we detected so many bursts, question is how much energy does the single engine have to this source, long life and hyperactive source alive. So we try to estimate the total energy of this source using this formula, and we split the operating duty cycle and assuming a beaming factor of 0.1 and the reading efficiency of 10 to the -4, and then we get a total released energy at around 1.347 times 10 to 47 Earth. So it's about 30 or more than 30 times the total energy, larger than any other active repeaters. So considering dipole magnetar, a typical magnetar with a big factor of 10 to 15 Gauss and a radius of 10 to 6 centimeters, the dipole magnetic energy of this magnetar could be 1.7 times 10 to 47 Earth. This is comparable to our total released energy. And so we place a lower limit on the single engine's magnetic moment. And it is about 86.5% total dipole magnetic energy of such a typical magnetar. And if we assuming a similar activity during all 500 continuous active days, it should be 122% of this total magnetic energy. So it should run out of the energy budget of such a type of magnetar. Our work for the present stringent constraints on models with the low radio efficiency, large beaming factors, and low energy budget models. This work is under review in the natural astronomy and also preprint at the archive. So we also try to understand the energy distribution of this source. We try to fit the cumulative energy with a power law function, but I should notice that this plot is on the log space and without error bar, which may overestimate the goodness of the fit. So for the directly the energy distribution of this source, there's a parasitic energy around 10 to 37 Earth, and it is above our 95% completeness threshold, and it decreases below the parasitic energy. So we try the power law of it above this parasitic energy, but it doesn't perform well and shows a variable power law index. So we try to fit with log normal function and the bimodal log normal functions. The log normal function also does not fit well. It shows divisions and it shows normalized polarization, Pearson coefficient and residuals, and it is better with a bimodal log normal function. So the energy distribution shows complex structure with two components. And since we have a number of experts to do a detailed analysis on the energy distribution, we try to narrow the binding of the energy distribution, and it shows a clear valley and bump structure around the 5 times 10 to 37 Earth with, and this structure we are doing the calibration and energy analysis and also significant test on this structure to see if it is a stable structure or it could evolve evolved over time. So here's a summary of our work. We detected over 17,000 bursts across 500 days, and it released an 86% diaphragmatic energy of a typical magnetar, and it should run out during all 500 days. And then we put a stringent constraint on all those with low radial efficiency and typical magnetic parameters. And we show a complex energy distribution with two log-normal components, and there might be a fun structure. That's all. Thank you. We also try to actually we also try to compare this actually of it shows actually X-ray and the fraction of X-ray, and we go about to lab. So we do the application of touch. They can make more
very nice. I was just wondering, very nicely, if require the things, then does this mean that power reducing power where the energy is not
our back is long indicate. So this could be our distribution
Hello, everyone. I'm Wenfei. Wait. Wait. Okay, I'm Wenfei Yu from Shanghai Observatory. I will talk about fast. No. Okay. I'll talk about fast 19 beam observations of the FRB 2024-01-14A. And this is observation program from the fast FRB KSP team. And okay, and so I would like to acknowledge my collaborators, Zhun Zhang, and also the KSP. And I also, because I'm using a customized ideal program to process the fast data, I would like to also thank Zhichen Pan during the process of handling fast data. At the beginning of 2024, Chime discovered the FRB, and then follow on the report from Chime talking about potential high burst rate because only they detect the burst from this source during only a 4-minute window, FAST started to monitor the source. And in early March, FAST detected really high burst rates up to 500 or above. And then we initiated 90 beam evolutions, and we want to study potential mini burst population that won't be able to see in other sources or with other telescopes. And we also want to study potentially transient or flaring events, which is different from bursts that might occur in these kind of FRB sources. And we also want to study potential burst contribution because the burst rate is too high and the flux from bursts can be significant. And we also want to probe the burst engine because during the high burst rate observations, the burst rate is about occurs every 6 seconds. So we are able to probe the central engine through study the correlations among those bursts on really short time scales. And we also noticed that we might be able to potentially localize the burst source just if the burst flux contributes a lot. And this was actually considered before the Meerkat's initial localization. This slide, the version of the 90 beam show on the right. The central beam is on the source, we can detect the burst, and the other 18 beams are observing nearby field of view. And on the left, I showed the light curve. It is first also calibrated. And the black one is the beam on the burst source. And we can clearly see the light curve. We can clearly see variabilities across those beams. We can see the burst. And so I'm going to talk about our pulse spectral study, Fourier pulse spectral study of the time series or the burst change. Okay, and so we studied the pulse spectrum. I'd like to compare two observations we performed, not only the one on March 10th, 2024, we also performed during another kind of outburst on 2025, January 1st. On the top row, I show the pulse spectrum, which is the Hall times frequency versus frequency. And the middle row shows the radio spectrum, which is the pulse spectrum of beam 1, which is under FRB, minus the average pulse spectrum from the other 18 beams. And the third row shows the pulse spectral ratio. So the main result is that we see the pulse spectral contribution from bursts. It's a prominent component, roughly in the range of 0.1 hertz to several hundred, up to 600 hertz, and it's broad. And we can also see, because the burst rate, the difference between the two observations, we can also see what's the effect of the burst rate. You can see that the power of what I call is the timing band limit noise. The power of this band limit noise is higher during high burst rate episodes, more high burst rates, higher burst rates correspond to larger power. And also for high burst rates, we also see the band limit noise is broader towards higher frequencies or towards the lower frequencies. Okay, so let me summarize this. The burst change constitute timing band limit noise, roughly in the frequency range of 0.1 to 600 hertz, and higher burst rates belong to a broader and stronger timing band limit noise. I would also like to specifically show in the pulse spectrum is no power actually exists below 0.1 hertz. Also, that simply means that the bursts with intervals larger than 10 seconds, they are random or they are not correlated. So there's no waiting time among those bursts. And the other thing is that actually there's no significant power exists above about 600 hertz, which also means that no statistically significant sub-millisecond variability exists in those burst chains. So we can apply this knowledge to for our longest observation ever taken. Okay, the longest observation ever taken on this FRB source, which is on 2024 March 12, is 4 hours, and we can remove the low frequency part, and we can show directly the bursts, and this helps us to do some further studies. Further investigation shows the band limit noise is frequency dependent, and I already show the band limit noise is burst rate dependent. And I also try to do more experiments with the data. On the right, I can experiment on the burst chain. I can take away the brightly bursts one by one, and I can see what the pulse bar shows. And this really shows that there's a frequency contribution from the bursts. The bright bursts contribute to more power, but at slightly lower frequency to the band limit noise. Okay, so I go directly to my conclusion. I think it's simple as no significant power like below 0.1, but it simply means that the burst occurs randomly, sometimes so longer than the band limit noise. And waiting time of the engine doesn't exist among those bursts which separate longer. And also no statically scaling subness and variability, like we can see in these observations. And also the detection of the band limit noise. So I'd like to mention that because of this band limit noise, when we claim detections of periodicity or quasi-periodicity, has to be tested against this timing band noise instead of just test against white noise or red noise fluctuations. And my conclusion is that the timing band noise is an indicator of the burst engine, and it will help us to form a timing picture of the burst engine. And to just mention more is my collaborator, Shen Zhang. He works on the FRB's radio continuum counterpart. You may chat with him in the meeting. And also my another collaborator, Xing Yi, Dr. Yi Xing. We have also tentative gamma ray counterpart, and you may chat with her as well. Thank you very much.
It's nice to pages. And
Oops, sorry. Hello everyone, my name is Ninisha Manaswini, and I am a third-year PhD student at Max Planck Institute for Radio Astronomy, working with all these amazing people. And today I will give you a brief overview on the polarization position angle variation on this particular FRB 2024-011A, on which we don't think we need any introduction because we have heard a lot of talk about that. So polarization study has proven to be one of the most powerful tools in probing the FRB emission mechanism and also the immediate local environment. So after correcting for the Faraday effect, we see that for some of the FRBs, the polarization position angle is varying. So we thought this can be coming from the two of these phenomena. One is intrinsically the burst might have different polarization position angle, or there can be some of this propagation effect which is causing the orientation of the individual burst PPA to vary from one another. So to study that more further, we observed this particular FRB 2024-011A with two of these telescopes, Nancy Radio Telescope located in France and Effelsberg Radio Telescope located in Germany, with the help of all these collaborators. And the purpose of using both of these telescopes is the frequency coverage being the same. Both are falling in the L band, and also it can act as a check source in terms of the instrumental allocation, which is most important for the polarization study, and also can act as a check source for our results. So in total, we have recorded over 900 bursts using both of the telescope within 1 year of the time scale. So here, directly jumping towards the results, like these three bursts I am showing from one of the epoch in January 2025, within a couple of minutes of observation, most of our bursts are highly linearly polarized with some fraction of circular polarization. However, if we only look at the upper panel of this burst, showing the polarization position angle, we see that it is varying from burst to burst. Now, to study that in a more exhaustive way, let's stack them together side by side in the same fashion that the bursts have arrived. And here I am showing the different colors as different bursts, so as the vertical gas line. And the gray highlighted region shows if two or more bursts have happened within 1 second time only. So this is one of the epoch from March 2024 from Nancy Radio Telescope. And here we see that the polarization position angle within 60 minutes of time are varying arbitrarily without any particular trend. Now I will show you some of the other epochs, and we will see how that is varying. This is another epoch from, again, March 2024 from Effelsberg Radio Telescope, again showing the same effect. So here is the last epoch from March 2024, and here we see that the PPA spread has confined to a more stricter region than we see the before. Now let's jump to the next hyperactive epoch, which is July 2024, and here we also see that the PPA spread is quite small compared to the first hyperactive epochs. So these are some of the epochs from July 2024. However, if we again move to the December 2024 epochs, we again see that from the burst to burst, the fluctuation in PPA is again varying within -90 to 90 degree without any particular trend. This is January, again another epoch in January. So to study that further, we have defined two metrics. One is the delta PPA and another is PPA 0. The delta PPA suggests how the relative variation in between bursts in PPA happens, and the PPA shows PPA 0 shows how the individual burst polarization angle varies from its average mean of that particular epoch. So here I am again showing the same thing. The broken axis basically shows the three hyperactive regions. The violin shows the spread in PPAs in those hyperactive regions. And the color bar shows the particular telescope mentioned in the legends. And the number of bursts that we have taken into account to study this are shown in the upper panel. And this is the dataset from 13th of March 2024 until January 2025, so almost a year. So as you can see that the PPA variation is happening. The first and third hyperactive epoch, the spread is larger compared to the second hyperactive epoch. So there has been some of the observational conclusion that we drew from this study, that the distribution is symmetric about 0, and we see no statistical significant dependence on the burst separation timescale. Even though the burst rate is varying within these different hyperactive epochs, we see that the most of the bursts are highly linearly polarized with some fraction of circular polarization. And the 90-degree jumps, which we know as orthogonal jumps, are very rare, just one in our entire data set. Now let's compare to what we know so far. So these are the first and third hyperactive repeating FRB, which are still bursting, by the way. And we see that for the first repeater 121102A, within epochs, the polarization position angle stays the same. However, for the third repeating FRB 180916B, within our time scale, within the same epoch, the PPA spread is the same. However, if we move to these two FRBs, 211124A, the PPA spread is there. On the other hand, for the 240114A, we see the spread is getting larger with respect to no clear indication of any trend. So what do these observations imply in our data set? Given the fact that we see the PPA jumps are there within millisecond to second time scale, so the faraway models have some difficulties in explaining this arbitrary PPA fluctuation. Hence, if we move to the magnetospheric models, there might be some kind of emission mechanisms which are causing these arbitrary PPA jumps in terms of any kind of geometric effect, or if we consider there are some of the different emission sites which are causing this burst to have different PPAs, or maybe some multipolar magnetic field. Now let's move to the propagation effect. This can also cause this type of PPA variation. However, if we want to disentangle between the intrinsic emission mechanism and the propagation effect, then the solution might be lying in the broadband observation of this particular FRB, which we are doing now with one of the imaging receiver we have in FSO radio telescope, the ultra broadband receiver. And here I am showing one of the single pulse from magnetar 1810, which shows the frequency bandwidth of our receiver going from 1.3 to 6 gigahertz. So this work is currently ongoing. So now I will try to wrap up in terms of what we have observed. So we have done a long-term monitoring with these two telescopes for 1 year. We see persistent burst-to-burst PPA variability within epoch. And this PPA variability is also jumping around within different hyperactive epochs. So that there are some difficulties in the current models. And maybe the broadband study will help us to know more in detail. Thank you.
So we found those episodes where we see more variation in position number, and then episodes where we see less. Does this correlate with anything, maybe with the overall energetic stability during those episodes?
Other correlations such as linear or
Meaning those times when we see a big correlation, and there also episodes where we see a lot of output, energetic output from the system compared to the other cases where it's in
what way is slowly getting, but I'm not sure about the initiatives. However, the period was for the entire 1 year from answer to this goal very difficult.
Two critical issues in your accumulated polarization law. One is how do you align different poles in different states? We don't know whatever poles some poles have a later phase polarization angle. We don't know. That's a big issue. How do you align all different poles in the same pole? This is right. Second, the polarization angle, where have you just how to say corrected all the problems of this metal, including ionosphere or not, for example, ionosphere of this metal, or in which frequency, for example, we give the infinite frequency or whatever. So this is the two critical elements we have to clarify on the point.
Yes, so
in 2 minutes.
Yes. So
the question is, I think that I have seen all the picture, so I have basically contaminated all the body. In the same area, we have analyzed. And all the polarization position until analyzed to the similar frequencies. And I have not shifted for the ionospheric position measure. And these are all the first that are related for the first specific position measure and also for the average position measure.
So that have to be careful because we do all the quantity different levels, you have to collect everything, have to be careful of that. I understand how to align the post. That's how we say you always align the post from the left, right? The left to right. That's okay. But the transition is probably you have to be careful to get everything.
Okay, like if you want to this is kind of getting the rejection digital of and find residual and we found that at the fixed that's probably appropriate of perspective.
能考吗？
这能考。